Thank you.
Okay. For those who know Jeff Campbell, here's Jeff Campbell, my spatial remote sensing contractor at work. And this is, there's several of us in the science team. There's Sarah Beyer, Kevin Baddick. I forgot Michael Clifford, who did contribute to part of this. And Anna Richards from Australia is a guest in our office, and we had included her on this. Okay, we're going to have three parts to this. So there's three distinct sections, and they all revolve around ecological departure in some way. I'm going to explain how we couch this in terms of landscape conservation forecasting and its products. So it's basically maps, models, and metrics for large landscapes, and the metrics is the ecological departure component, but there's other kind of metrics I'm going to briefly mention. And this is the South Snake Range, where Great Basin National Park is located. So the whole landscape conservation forecasting method is summarized in this one slide. It's maps, models, and metrics. And we do our own remote sensing, and I'll explain, I hope I'll explain, remember to explain why we do that later. But when we do our own remote sensing with high resolution imagery, we do the first ecological system, so that's the equivalent of BPS, and the vegetation classes, which is the S classes. So we try to use terminology that our partners recognize often. If you take that black arrow on the first map there and you point at a specific pixel, whatever resolution, it corresponds to an ecological system. And this ecological system, we represent it by description, but also by a state and transition simulation model. This is the SynchroSim software. And I use here a small state transitions simulation model because I could fit it on a PowerPoint slide. The second map, if you go to exact same pixel, will tell you what is the vegetation. So that's that purple arrow. And in this case, this happens, I decided this was a saline meadow. And the class in the lower graph is an annual grassland. So this was invaded by cheatgrass. The three first boxes here, I don't know if you see my cursor, are the reference classes. And these are all uncharacteristics. We map to great detail the uncharacteristic class because most managers manage uncharacteristic classes. They don't often manage a reference class so much. Sometimes they do, but often in rangelands, it's the uncharacteristic class. So we need to know what they are. So if you have 25 ecological systems or 40, then you have 25 or 40 distinct state transition simulations models. And for example, our Wyoming Big Sagebrush models has 53 boxes in the state transition simulation. And the beauty of these state transition simulation software, it can be non-spatial or it could be spatial. We prefer spatial, is that you can start asking questions of what if scenarios. So you, as in NEPA forest planning. So, and this is how this was born, this thing. You can say, what happens if I do nothing special for the next 50 years or 25 years, the lifespan of a forest plan for 20 years. And you can say, what happens if I do management alternative A, B, C, and these have different names and different themes, and then you compare them. And that's what we did here. And in this case here, so with these what if scenarios, you get results. And now these results, you calculate metrics. And what you have there is vegetation departure in that, you know, green is good, yellow is intermediate, and red is bad. We took focal systems. So we had several systems in this landscape, and the partners we work with at the BLM picked a few of those that they wanted management on. And then we did we took the current for our own remote sensing. We measured the departure in the current. And then we did minimum management for 25 years. And we measured what happens if you do nothing special. And we also did this for another landscape. But so this is your traditional. So this is built in the software we have. In the SynchroSim STSim software, there's an add-on that's called ecological condition or reference or something like ecological departure. I always forget what it's exactly called. But we do other metrics. So some of our partners will ask us about habitat suitability for a species. So here we have a metric of habitat suitability for greater sage-grouse where we managed for 35 years. This is active management. And then we calculated what happens to suitability after 35 years of management. And we compare that to the no action scenario. I'm not showing that. Don't want to make this too busy. But in some cases, we did carbon stock and flow model. I've done that. Social resistance to fuels management. We're doing that currently on a project. We've done hydrologic resource measure, the increased runoff or recharge due to forest management. So that's something we've done and are doing. So to date, we have probably done 20 projects, and you'll notice in the east, close to where Jean lives, we did the Cherokee National Forest in something like 27, 28. Nature Conservancy with the Tennessee chapter, I think the North Carolina chapter, and with Greg Lowe was the one doing that, and I was revising his models from Reno. So it's so far we've covered 1.9 million acres that we've actually mapped with remote sensing, and we done active projects for. The resolution range from 30 meter. If the customer doesn't have much money, it will be 30 meter resolution with Landsat, but we haven't used that in so long. And then currently we're using 65 centimeter. We like the Spot 6-7 satellite at 1.5 meter resolution. That is pan sharpened, auto rectified and everything, multispectral. All of our work is done with partners. We don't do any work that is not with partners because we need numbers and data from the partners. And our partners are typically the Forest Service, the BLM, National Park Service, Department of Defense, private industries like the mining industry, and ranchers. This work has now been published, as you can see down there, and the last publication in the journal Climate 2021 is the one you may want to refer to. And why this? So this started a long time ago in 2003 with the Ely Ranger District, so the Forest Service, and they said, we love working with you. You guys bring good snacks at our workshops and all that, but what you're giving us is not useful for forest planning. And they said, we need a method that you will develop that has alternative scenarios with different actions. So alternative A, B, C, D, and the no action alternative. We need a restoration budget cost, unit cost per acre. We need cumulative impact assessment with fire years. We need distinct fire years and no fire years, and we need a measure of return on investment. So this method was born from these people. Some of these people are now retired. Some have passed away. Some have gone to other jobs. And all of these managers typically ask the following question. What is the current condition of each system or focal species in your landscape? What is likely to get worse using current management? What potential strategies to improve degraded ecosystem or focal system can you devise? Can you make up? And let's test those strategies because people can dream up strategies. They don't always work. And the simulation that's why we test the strategies. Ultimately, time will test, but when you don't want to wait 30 years to get a result, you simulate it. And which strategies produce the highest ecological return on investment. So I'm going to give you some sense of the products we deal with. This is an example. So this is all derived from ecological departure. And you are managing certain class of vegetation to recruit another class of which you have a deficit in. So you're moving the acres among what you guys would call the S classes. And here is one for one system. It's Utah Service Berry. This was in southwest Utah. And you have different actions here in the rows: chainsaw thinning, masticate, prescribed fire, small tree lopping. And then you have in the second column the cost per acre. This is a long time ago. This was 2012, 2013. And then the managers want us to have the first 10-year implementation phase. So these are the acres per year of these actions. And then they said we want a second implementation phase from year 11 to 25. And that's more the maintenance phase. And the software gives you the total budget you spent doing that, which was around $450,000 over this 25-year period, just for this system. So you have to realize this adds up. So this is derived from ecological departure. And also what we have is that when we do these simulations, we always have a budget. And in this case, for Boulder Mountain, this is a photo of Boulder Mountain here. It's between Bryce Canyon National Park and Capitol Reef National Park. So the two ends, the southwestern end and the northeastern end of this project that you see there, is squeezed between the two national parks. This landscape is approximately 700,000 acres. And then we did the remote sensing for this with Spot 6 satellite, 1.7 meters. And they said for the management, and this is two distinct national forests that came together to share their resources on this important landscape for big game. It's really important for big game. It's a high plateau. And they said your budget per year is going to be approximately $1.5 million. And we had in the room the decision makers and the supervisor of the national forest, and they all agreed for this important landscape, they could, based on the experience with other landscapes in Utah, they could pony up 1.5 million acres for management total. So we tried on average to respect that, and we did a pretty good job. One of the products you get from ecological departure partitioning and figure out where the treatments go with spatial simulations, the software will spit out a frequency raster. We do Monte Carlo simulations. So we do the actions and we replicate them with different climates and all that. So we have distinct climate scenarios. And the software will tell you where is the highest frequency of, for example, in this case, of that you should have, where you should put as a manager, prescribed fire, masticate, spot herbicide and seed, or feller buncher. And here we are. We just did this project not long ago, and there's already actions that are happening on the ground. One of my partners sent me a photo where they started doing the feller buncher operations in aspen mixed conifer that you see right there. So this actually already led to action on the ground. Typically, what people ask me is, how much did you contribute to restoration? And I know we're running in the 300,000 to 400,000 acres simulated, managed, restored now, not simulated, but restored so far. And I don't keep track. So we by the time I retire, we're going to be close to 1 million acres probably. Other metrics that I mentioned in passing, so I'm going to go fast because this is not departure. This is a suitability with greater sage-grouse. So Kevin, we use a University of Nevada, Reno, a statistical model of sage-grouse habitat suitability based on 10 years of field data. Kevin, with the postdoc, converted that to an R code, and the R code determines where treatments get implemented in the landscape in areas of intermediate habitat suitability. And this is a small portion of this 880,000 acre landscape. So, but basically you can show that restoration increases suitability. We've done carbon stock and flow. So we showed in this geography, you see a map there that was produced by Sarah Beyer with Sentinel. That's 120 million acres. Sentinel 2, maybe 3. And with Google Engine and a random forest model. So she simulated that and determined the cheatgrass cover. And you have beautiful examples here of cheatgrass dominance. So this crap that you're seeing in the photos is monoculture, is pretty much a cheatgrass. And we did one action, is seeding to perennial species. And then we measured the net benefit from seeding perennials in this degraded landscape. And we had metric tons of year per year of carbon sequester. And we showed that you actually, this is published now, and that you can actually sequester carbon even in these dry environments, and significant amount of carbons in the soil. This is a paper Kevin Baddick led, but basically this was in the Tahoe National Forest in the Humboldt-Toyabe National Forest. So that's Lake Tahoe you have there. We did 6 scenarios: control and aggressive forest thinning, combined with 3 climate scenarios, a historic and 2 global circulation models. We did this for 60 years. And in this specific case here, we determined what was in the first graph, the stand replaying fire risk. In the second graph, we did a sedimentation model where we're able to show where was the greatest potential for soil loss to the riparian systems, to the creeks and all that. And if you combine the two, it gives you management priorities for where you should do the action based on the objective of sedimentation. If you have other actions, you'll have slightly different shape files. And then we did hydrologic stuff where we actually working with Flint Hydroscience. We're using the USGS basin characterization model. So we did this project here. And what basically they did is, once we calibrated the basin characterization model, the hydrologic model, they did a magic wand exercise. This is ongoing work, by the way. They took closed canopy of Jeffrey pine that looks like ponderosa pine, and they thinned them by 50%, so 60 to 30% cover to reference condition. And they were able to show the increased runoff and recharge between 5 and 87%, and that depends at higher elevations, and in deeper soil you get more recharge and runoff, and you get less at lower elevations. So this is these are these kind of other metrics that we couple with these systems. And this is not based on departure. These are other metrics, just to know that you can do more with this approach. So this is this part here. I'm going to stop on this is the general context from where our team comes from. We do this for a living. We're like contractors for hire to do this pretty much. So we work a little bit throughout the West and all that. There's no question. So this is an obscure topic that you will relate to. It's the Unified Ecological Departure, and this is actually coded into the SynchroSim SDSIM software. And this is work in progress too. It's old work, but I'm revising it now. And I'm going to go short on this because this is going to be revised. But basically, we had both our Forest Service and BLM, Bureau of Land Management partners, were a little bit annoyed with the traditional ecological departure because they said, we have old seedings of crested wheatgrass that were done in the 50s and 60s and 70s that are actually now some of our best habitat for wildlife. And they said, we're getting penalized because it's an uncharacteristic class, but it's actually beneficial and it's functional. Is there a way to give us brownie points so we're not penalized when you do the uncharacteristic class calculation that you guys saw that Jim Smith and others showed? And they said some noxious exotic forms are way worse than cheatgrass, and we want them to make them worse than just uncharacteristic. And we still want a single metric. So basically, oh, and by the way, here you have a photographic interpretation of an aspen woodland historic range of variation, where the size of the photo is proportional to what the class should be in the reference condition. An example of this is simplified model, where the first is what you observed on the landscape and the expected of the historic range of variation on this boneheaded simplified model is there. But basically, we have in the first row, early successional, later successional, then we have cheatgrass monoculture. Then we have one of those crested wheatgrass seedings that's actually used by wildlife and it's functioning very well. Not only that, but it's undergone succession. And there's a full complement of sagebrush in it. It's functional. It's used by pronghorn, sage-grouse, and whatever you want. And then by that, our old Jeep Cherokee, there's that beautiful Russian knapweed all over the place. And they said, that's bad. The crested wheatgrass is acceptable to a point, and the cheatgrass is not acceptable, but it's not as bad as Russian knapweed. And this is what they said, we need to fix this thing. So we invented this that I don't want you to pay too much attention to, but in the first row is the formula of ecological departure that Jim Smith was, with the minimum of each row, 100 minus the sum of the minimums. So that's your standard formula for vegetation departure. What we did is unified ecological is that ecological departure score plus a badness factor minus an acceptable factor. And the badness factor is, the Russian knapweed factor, and the acceptable one's the seeding. And we're going to skip the rest part, all the math that's in there. It's actually a little bit more complicated than that because we are revising that right now. But basically, this metric is in the STSIM software under ecological departure add-on. So you have to supply 3 tables: the HRV, the threshold of acceptability for seedings, and for non-native seeding, so introduced species seeding like crested wheatgrass and intermediate wheatgrass and all that. And you have to define the badness level of these exotic species. So we've done that, and it works, but I'm not satisfied with the formula there that I came up with others a long time ago with. So the next steps we want, some of you want to see a photo of Greg Lowe from the past, and we're going to overhaul this formula. I want something simpler that's more continuous. And it's going to be, and I'm working on it right now. So it's going to be ecological departure multiplied by correction factor. Get rid of all these min-max functions, because I didn't show them because it just makes everything clunky. And I started a prototype and I showed it to the staff and they nearly vomited, but that's all right. That's, it's a work in progress. So, but anyway, it's going to be a simpler formula that's more continuous form. And that's all I'm going to say about unified ecological departure. But this is something that someone mentioned earlier. What happens with these exotic classes? They feel this is exactly why we did, and we would never have done this if the managers had not asked for it. So, and in the special case, when you zero out the 2 columns in the menu of SynchroSim STSIM, and you just specified the historic range of variability, by definition, it goes back to the traditional ecological departure calculation. So ecological departure is a special case of unified ecological departure. If someone wants to ask a question about this would be the good time to ask, because now I'm going to go to the spatially explicit stuff, which is the fun stuff. Oh.
Yeah, no questions at the moment in the chat, Louis.
I know I'm talking fast, but this one, I'm going to go a little bit more slowly on it. So, all of you know that the traditional measure of ecological departure, we call it ecological departure, and you call it V departure. It's the same thing. It's non-spatial and it's not stochastic. We want to develop a spatially explicit ecological departure with a moving window process. So you define your window and you calculate, all your calculations is done in the window. And what we want is have the ability to specify a distance decay weighting so that more distant pixels count less in your estimation. So now imagine you're thinking like a wildlife species, and something that's far away is not so relevant to you. Or if you're a manager in something that's far, far away in another galaxy, is not as important to you, unless you do time travel, of course. But it's that's the process here. And also we want a stochastic version of this. Now, Corey and Randy Leonardo's, and I don't know if Jim was part of that, did work on a non-spatial stochastic version of ecological departure, and that was published in 2015. This is a recap. Jim Smith talked about this, but I gave an example here. So ecological departure, just so everyone's not confused, is that vegetation departure for the new LANDFIRE and the new version of LANDFIRE, which is the old LANDFIRE was fire regime condition. We don't use that terminology anymore. But there's the formula, 100 minus the sum of all the minimums of each row. And you have here the two columns. And Jim Smith, the very first day, says, what we want to know is the dissimilarity between these two columns. I took mountain big sagebrush here, and I did the 5 succession class. So I did specify what's the cover of shrubs, trees, and herbaceous stuff. So these are mutually exclusive classes in one factor. We went out there and we actually did the satellite interpretation imagery, and we did the models of the historic range of variability models. So we got the reference. So expected is reference, and observed is what we got from the satellite. And then there's the U class, which is this hodgepodge of classes that none of them are equal to one another. So this model here specifically has 20 uncharacteristic classes. So there's 5 reference class, and there's at least 20 uncharacteristic classes. And they all add up to 38%. But basically, as a manager, your job is to know that, and Jean was talking about this for Virginia, is that you have too little of some class, like you have too little of early successional, in our case, mid-successional, due to fire exclusion or grazing or whatever. And you have too much of this late successional stuff, so a little bit of fire will help, and you have too much of some of this uncharacteristic class, and your job as a manager is to move from green to red some of these acres. You won't be able to, within your budget and all that. The problem is when you have traditional ecological departure, you can look at this landscape. So this is one of that 880,000 acre landscape we worked in. And the boundary of the project is administratively defined. And I picked here in these 2 arrows, black sagebrush. And this, you may not realize it, but there's nearly 30 kilometers apart between these 2 arrows. These are big landscapes. So entire states in the eastern United States fit in this one landscape, just to put in context. But for traditional ecological departure, you have the same score over there and closer by. There's only one value for black sagebrush. It could be 56% or whatever. But as for management, it's not very practical. First, it's administratively defined, all that. The sage-grouse population that's in the forward arrow is distinct from the greater sage-grouse population that's in the back arrow. It's not the same population. So there's this different subpopulation, I guess you would say. And the agencies and the partner says, we want something that is more local to endangered species management or TNE species management, and think of sense of perception. We want to have, what's over there doesn't affect my decisions for management over here. So, and also what bothers everyone, and especially me, was that there's no stochasticity associated with the reference condition. I do these models of reference conditions I simulate for 1,000 years, and there's no stochasticity, there's no estimate of variance for the historic range of variability, and that bothered me because it varies spatially and it varies with different future climates. So what we did is for each system, we use the same equations that we use for ecological departure. So basically what we say is that our universe is going to be defined at a pixel ij, and there's a circle around it that you define, and that's your universe. So in that ij, you have the radius to all the way to mn pixel. And in this radius, you actually you have a historic range of variability, and you have the proportions of your class. Our moving windows have more pixels than the one cartooned here, so just realize that this is a cartoon. But you go pixel by pixel, and each pixel is your focal pixel is your universe, and around that, and that pixel will get a value of ecological departure using that 100 minus sum of the minimums formula in there. The pixel is, we use the home range of an animal species often, TNE species. So we have different sizes. This one, I don't remember what we did for tumbling JR, but you'll get an example for another one. And the user specifies the shape of the function. This is an exponential decay function. So the farther away the pixel, the less important it is to the animal species or the manager for that matter. So you have the ability to define that. And if you make a flat curve, then you revert back to the traditional calculation percentages for ecological departure. So that's the special case of it. And the proportion is just the sum of the weights. Each pixel has a weight. It's farther away, and you just sum. So you go to pixel M and N, that has a weight, and that's your value. If you were doing traditional ecological, that would just be 1 or 0. It's either in or not the same system. In our case here, it's a weight, and it's far away at the edge of your moving window. It doesn't contribute a whole lot, but it's really close to the IJ pixel. It contributes a lot. You just sum the weight of the pixel, and then you sum it across all classes. And it's the proportion for that class only and only in that window.
Yeah. So one sec, Louis. So Jim was leading us through this yesterday, but at that scale of the map unit. So we're essentially just doing that for every pixel in the landscape. And then doing some fancy accounting using that distance curve to get the proportion for that focal pixel. And from that, we can calculate the departure. It's super computationally expensive, and I'm still working on like cutting down the time that it takes. But the maps it makes are pretty cool. And that way you get every pixel has its own unique departure value. And then there's also a lot of things that we can play with here, and that's being the radius that we're considering. That could change. We could also work with the distance function. That's something that you could also play with. And then something that I would like to also start considering is topography. So thinking about barriers that would affect that distance, being like cliffs or highways. Yeah, those are just my thoughts.
Great. You spoke like a true coder and geographer. So this is the landscape we first did. And what you guys may not know, I didn't talk about yet, is that Sarah and I took Sarah did the GIS, I did the interpretation, took all the ecological systems in there, and they're all listed there. And each uncharacteristic class or system was converted to the most likely ecological system and the most likely reference class. So we eliminated anything uncharacteristic, and we created a pre-settlement landscape. So everything that was a mine, a road, or cheatgrass was converted to the most likely pre-settlement vegetation system and class. I simulated this in SDSim for 700 years, 20 replicates of the reference condition, the spatial reference with wind direction, topography, fire spread, the whole 9 yards. So all the realism you can do. So which means that the spatial, the reference condition will change in space, depending on obstacles for natural fuel breaks and things like that. And the temporal variability was a climate. So to estimate the variability, so the 20 replicates is your source of variability. We use the variability among replicates. We don't use the variability within one time series to do this, because that is autocorrelated. So you have to use, and this is what Corey and others did, and Randy and Leonardo, they also used the variability among replicates, not within replicates. That's not a good idea to do that. So here's an example of 4 of the 20 replicates 700 years later. And they look all very different and all that. There's some weird things that we fixed on this, but I like this thing. They're all very different. This is all the reference condition, but these are 4 very different reference conditions, and they're all valid. So this is the future. You don't know what's going to happen. Different climates, and they're all responding to climate and topography. And the proportion of the reference condition is just calculating with that moving window thing we just showed you when Sarah was talking about that. It's the same equation. But this, you get an HRV with distance weighting and decay functions and all that in the window. It's calculated the same way. So your HRV is defined at the pixel level, and it's surrounding around it. And once you have that, then you have everything to calculate ecological departure, because we had the calculation of the observed. We have the original, the map. And now we have the proportions for the HRV, and we just calculate ecological departure. And here's the result. So basically on the left here is the traditional vegetation ecological departure. It's non-spatial, it's not stochastic, and basically high is brown, yellowish is medium, and low. We know some people are colorblind, so we try to avoid the same exact colors, but it's difficult sometimes. And on the right, you have the spatially explicit and stochastic ecological departure. You'll notice this change. So some systems, like down here and up here, this is the same mountain sagebrush system, but here the software decided this was actually in really good condition. But the same system was really bad there. And this is higher elevation than that. So the mountain sagebrush now has different values depending on location and on natural fuel breaks and all that, and deviation due to the conditions there. And this allows you to actually know as a manager where you don't need to spend any money and where you should spend money. And this is great. And the other graph is actually the variance, the spatial variance of each pixel associated with the 20 replicates of the natural range of variability. So this is what this is. So this was our first attempt. There's a lot of R coding and some Python. And since Sarah has improved the coding and gone more to Python. So just in all frankness, you need to do Python for this because R is too slow and too memory hog for this kind of calculation. This is multi-system. Now, you guys may not know this, but in LANDFIRE at the beginning, there was the multi-system ecological departure. It was a weighted average, basically, of the single system ecological departure. It's never, I don't know if anyone used it, but we did it here. The reason we like this one is because imagine you are a Nature Conservancy employee, for example, and you're buying land somewhere in the boonies. And you walk into this land, and you're not just going to look at Wyoming sagebrush. Oh, that is in low departure, I'm going to buy this land. You're looking at the riparian system, the greasewood, the wet meadows, the different sagebrush. And this actually gives you an idea of what you are buying if you're doing a protection action, or if you're thinking like a mule deer and you're sampling all the vegetation. This is more natural metric if you're thinking like an animal who's using all the resources available. And it's the same formula, except you prorate it to the proportion of the system within the moving window. And you get a measure of ecological departure for that. And you get a measure of variance too. And the variance was quite low in this case. So there's a lot of consistency between replicates. And the previous slide, you'll notice the variance was actually quite low too. So this is really stable results. We really enjoy this. So this was our first attempt in the tumbling JR landscape. And then, oh, Sarah, you may want to talk about this. Yes.
Oh, this is just Corey, what's up?
Can we go back a slide, Louis? I just got to ask, so when you set this up, I thought you were going to say you were going to get like a departure score for the whole landscape for all the systems, but that doesn't look like what's happening. Can you give me just like the real basic again on this?
Yes. So you are sitting where you're sitting in your chair right now in Bend, Oregon, and you're asking the question, I'm going to do a radius of 5 kilometers around my chair in Bend, Oregon. And you're going to ask the question, well, that's probably not a good landscape. It would probably if you were in the Deschutes National Forest. But anyway, and you're going to say, how departed is this landscape based on all the ecological systems around me sitting in my chair? At that pixel.
Assuming you utilize all of them a little bit.
Oh, for this metric, you have to. You have to. Okay. I mean, you take out the cities and the roads and all that, but you do have a historic range of variability in there. Now move your chair by 5 meters and go by 1.5 meters, and you're in the next pixel, and you redo this calculation. So your 5 kilometer window just shifted by 1.5 meter and on and on. So you're going to mapping ecological departure in the entire landscape, but the measure of departure is right there at pixel I and J in, XY coordinate. And now imagine you are a mule deer and you need in the same day serviceberry, wet meadow. You need to browse on Wyoming sagebrush of 4 different species and all that. So this is what you want to do as mule deer. is how good is this patch around me? And then if I move over there the next in the afternoon, how good is that patch over there? And this is what it's doing. So you have, as a user manager, define your search radius on this. But you cover eventually your whole landscape. Now, if your distance decay function is infinite, like it's to the edge of the landscape, and there's no decay, then this formula and ecological departure formula are one and the same.
Okay, thank you.
And that was true of the other one, except you would have just done one system. So your poor mule deer will just have eaten one shrub for his whole life and died of starvation or something like that, or malnutrition. Okay, Sarah, do you want to talk about this? The reason this is here is that the coding, you have to be careful on how you code this. And this is where Python allows you to do this far more efficiently and faster than R can do it. So, but
I use a combination of both, just because I'm a little more comfortable in R when it comes to like giant tables and very complicated accounting and keeping things straight. I have a whole PowerPoint because whenever I stop working on projects like this one for a couple months, I kind of forget how everything works. Then I have to come back to it later. But yeah, I've been using Jupyter notebooks for the actual moving window to get the values and the weights around each pixel. And that's done across the landscape 20 times for all of the different realizations of future vegetation. And that's the workhorse. And then after that, I kind of process and do the metric calculations in R. That's it.
And also, just so everyone understands this, the entirety of calculation is done by replicate. You do fully the calculation in replicate, then the replication, the calculation in the other replicate. You do not average across replicate until the very end when you're calculating variance, because then that's your population is the different replicates. We have now applied this to another landscape. So this is the same landscape in the Upper Truckee River Watershed, north of Lake Tahoe, that I showed you about sedimentation. Sarah, this is the version with more Python scripting than the Newark Valley project, the Tumbling JR we were before. And once again, there's the non-spatial, there's a single system, and then there's a multiple system, and each had their variance layer associated with them. So this is new, hot off the press. And this is basically went from going to R to this. The two landscapes are more or less the same size, I think, around the 300,000 or 400,000 acre landscape, 300 to 400,000 acre landscape. And in this case, the moving window was larger than in what we use for the Tumbling JR. This is 1 kilometer. It's the home range of a male pine marten. So approximately, it's like, I think Sarah said it's like 51 pixels or something like that, or whatever. But this is hot off the press. So, and the big black area, that's the town of Truckee. So it's the residential area and all that. But for this, we did replicates of the historic range of variability and all that. And then the resolution, so the Tumbling JR before had old resolution, and we were trying to make it go fast, so 60-meter resolution. But this one here, Sarah, is 25-meter resolution, if I remember well, or 20-meter resolution. So the spatial calculation thing was doing with pixels that were resampled from 1.5 meters to 20-meter resolution, because otherwise SDSIM and the Amazon cloud server and all would just burn and produce smoke and crash and things like that. But it doesn't matter. It's 25 or something like that meter resolution. But so this is less than a Landsat pixel. We are now working with Great Basin National Park, where we're going to apply this to 14-meter resolution, and that's a landscape that's equivalent to the size again in the 300,000 to 400,000 acre landscape. But yeah. So what we want to do is that we may want to generalize. This is future steps. So this is strictly ecological departure, or it's not unified ecological departure. And I'm thinking of, we may want to generalize this with ecological departure and with unified ecological. So that's not done yet. I want to rewrite the equation to make it more elegant and all that, if we go down that route. What is also needed is that everyone's has asked us this is, what is your search radius? That sounds very arbitrary. And how do you define that? And we were talking with Anna Richards from Australia on this, and she mentioned the species area curve you could use. So what is the size of a window that captures such X amount of biodiversity? And because Anna suggested, I have a photo here of Kakadu National Park in the Northern Territory of Australia. And you can also have species area curve among broad taxonomy groups like lizard and mammals, because you often have species area curve data for like mammals, lizards, birds, but you don't have it for fungi, for example. But this is kind of, if you have a biodiversity objectives like they do have in Australia, it's mandated. Or you can use the maximum home range among several T&E species, or you're just going to have to think about it. We just started this, so we know what we want, but we don't know what other people want. And this is all experimental. And the reason this all started is because this is what I was asking Lisa about the Forest Service hierarchical classification of vegetation. I have a desire to do what we call clustered systems, where they're lumped systems, but they're not simplified systems, but they're lumped. So you'll have like black and low sagebrush become dwarf sagebrush, as an example I gave here. But you have underlying spatial rasters that constrain the behavior. So the systems are lumped, but the ecology underneath is not lumped. And there's a way of doing this, and we prototype this. But the reason I want to do this is that the reference condition, when you lump systems that have different HRV and they change with elevation, suddenly your traditional ecological departure doesn't mean anything. You have to have a spatially explicit ecological departure. And this concept of working at very large regional landscapes with what we call clustered models, with complex soil-dependent spatial rasters that govern their behavior in spatial simulations, is what you have to do. But you have to have a spatially explicit ecological departure. Otherwise, you can't do it. It's meaningless. And CSIRO Australia is thinking about some of these concepts, and I think we should think about it more in our part of the landscape, especially with something like wide-ranging, like greater sage-grouse. But as geography increases, complexity increases, and we have to, as things get more complex, we have to find methods to simplify things, simplify and simplify. And this is why this whole process, why this whole spatially explicit stochastic thing emerged. That's it.
Wow, thanks, Louis. John, I see your hand up.
Yeah, no, this is really fascinating. It's the last slide that I did not show was just a question, and Louis and Sarah and team have provided an answer to that question, which was which is about scale. And so simply, okay, the forest, capital F forest, 1.8 million acres, has eco departure now. Great. But then an individual NEPA project, somebody developing an individual NEPA project says, oh, well, should we do an eco departure for our project area of 20,000 acres? And should we break that up by watersheds within the project area? Or should we, sometimes the project might be 3 disjunct polygons, and should we, do an eco departure for those 3 disjunct polygons? And we haven't come up with an answer to that. So this has got my wheels turning about coming up with the tiered down eco departures and why you would do that and how you would do it. So thank you for that. I'm still processing it all, but
yes. And you remember Randy was talking about, not just Randy, but Corey too, the map zones that determine, some of these sudden breaks in vegetation and things like that. With this, we do our own remote sensing. So we observe the biophysical, we know exactly where the biophysical setting is, and we know exactly. So in our case, there's direct translation, but there's no boundary in there's no edge effect, or I don't know, there's no administrative boundary that's causing something. We do our own remote sensing, so we take care of all of that. But what I think is that with this method, and I'm convinced of it, is that the size of your project area, influencing the proper NRV, HRV and all that, the historic range of variation, and these map zone delineations become irrelevant. It becomes a moot point when you use these spatial, because it erases all those problems. even if you have a change in ecological systems, it's localized and you can detect and explain it. So you even don't need to reinterpret systems. But also, if you have a landscape where you have a system and there's only 100 acres of it, and obviously doing a departure calculation 100 acres for a system that's more widespread is just ridiculous. I mean, it's so statistically biased, the number means nothing. You might as well just work with the raw S classes. Well, with this method, because you define locally the ecological condition, that 100-acre glade that you may have in an oak forest, you actually can assign a true, unbiased ecological departure value to it. So the size of the landscape is not important anymore with this method, because you generated, you generated your own historic range of variability given all these constraints on size and surrounding forests and proximity of cities and all. Well, they're gone. And so this is not an issue anymore. You don't have the statistical bias from small systems.
Yeah, great question, Jean, and thanks for that, Louis. I see Anna, then Jim have hands up.
A quick question, Louis, just about the variance, that those variance maps. How were you thinking of using those values? Like, where would they be applied, and thinking about the management of these systems given those multi-systems ecological departure metrics?
We haven't thought too much about that, but what we notice is the variance, the highest variance are in those areas of intermediate departure often. And what they indicate is that you should not hang your hat too hard on something that has a higher variance, because there's very different outcomes that happen there. So there's multiple solutions to management probably in there, and you should not fixate on achieving a certain reduction of a class too much there, just because what your desired objective or condition is not well defined there. There's multiple alternatives. So that's all it means so far. We want to know why it meant that and all that. But that's how I haven't had time to think about it too much since this stuff is rather new. But that's where I'm thinking, is that you should not get obsessed for areas of kind of intermediate departure if you also have high variance there. And also there's a reason that's happening there. And often that's due to a natural fuel break. The fire sometimes goes around your natural fuel break and sometimes it does not. And so it kind of gives you the idea why there may be that variability there, and you can do secondary checking.
Yeah.
Okay. Yeah. Thanks, Louis. And since my name was actually on the slide, I have to follow up with this question here, which is, I didn't really understand what you mean by basically collapsing the systems, but not the ecology. What is that?
Thank you. I'll send you flowers and chocolates for asking this question. I wish I had that presentation. Imagine you do a lump system that is called big sagebrush, and that is basically Wyoming sagebrush semi-desert, Wyoming sagebrush on upland soil, and mountain sagebrush on upland soil, and mountain sagebrush on mountain soils. That's an elevation gradient. But it's all the big sagebrush species. It's just Wyoming and mountain. I'm not even talking about black and low that are on different kind of soils.
Right.
Well, at the bottom of the hill, imagine you're on a hillside there, a mountainside. At the bottom of the hill, your fire return interval for the semi-desert system is 125 years. Stand replacing fire, obviously, in sagebrush. And the fire return interval at the highest elevation in the mountain soil of Mount Sagebrush is 50 years. So you can imagine the longer fire intervals favors later successional classes. And in the lowest elevation, not only that, you'll have higher natural and higher proportion of late successional class, but you can't have trees. Pinyon juniper, it's too dry for trees. But somewhere mid-slope, suddenly you have pinyon juniper. If you create one system that accounts for all the classes, then you have to have an underlying spatial raster that's connected to soil productivity that selectively turns off tree establishment. So it's zero value at the bottom soils. And then there's another raster that governs the fire return interval. And it's based also on soil productivity or other things, where the fire interval there's a raster and there's a multiplying factor that says, speed up the fire interval. Let's say 50 is 1. then depress it. When you go at the bottom of the hill, you multiply by 0.7 or 0.6.
Mhm.
So you have a 100. And that's where all the ecology of the system is captured underneath, under the hood by these rasters
Okay.
that the user doesn't see. We know they're there. We put them in the SDSIM, the SynchroSim software, but the user doesn't see those things. So it's like Jean was talking about his forest and the mesic and dry oak. Well, he could have a oak system. This is why when Lisa was talking about stuff, I was getting excited, is that you can have an oak system, and it's just called oak, pine, woodland, or oak woodland. But there's 5 different oak systems. You only have one oak model or oak pine model, depending on how you like it. But there's underlying spatial factors that govern each ecological processes of the system. And therefore, you can model this and you can calculate the historic range of variability for each pixel in the different parts of the gradient. So this is the advanced work that we're leaning towards. We've done a prototype and it kind of worked, but no one's paying us to do this. So it's out of unrestricted funds and we do this on the side. We don't have necessarily a contract. Actually, I got some funding recently where I can squeeze it in, but it's one of these things we do on the side. It's not our main job. So.
Okay, that makes sense, Louis. Thanks. Quick follow-up too, for those of you who are not as familiar with SynchroSim, that is the platform that most of us use for our state transition simulation modeling. Actually, it's a package within SynchroSim called STSim. And when Louis mentions a package, that's just an add-on that you're free to download or not when you download other packages from Apex, as the SynchroSim add-on. So once Louis paid for it, it's available to everybody. So just once it's there, you're free to use the UED add-on just by adding it to your SynchroSim platform that you've created. So we actually are working on trying to create other packages that would then be available for other things over time.
The ecological departure menu in the advanced menu of SDSIM was actually paid by the Bureau of Land Management. So they funded that. And other bells and whistles in the software is paid by Barrick Gold Corporation, some by the U.S. Forest Service, and some by the National Park Service. So that's how the software works at Apex RMS.
I will say that there's a LANDFIRE package, and that is to download all the LANDFIRE models in mass, which is what that does to create a library of all the LANDFIRE models. So that's an example of a package. And I think it's something that you should check back on if you use SynchroSim and see what's been added, because we are working on trying to create more of those over time.
And just to think, so people know, we're the science team of the Nevada chapter, but we're like mercenaries. So we actually work in Utah, in California. So people hire different agencies and people hire us to do this kind of work for them for their forest plan revisions or project planning or NEPA and all that. So we do venture outside the state, but we get less and less comfortable the farther away we are from the rangelands, So I work in Ponderosa Pine, all that, obviously on the Utah High Plateau and different parts around Nevada and the Mojave Desert. But we do actually help people, but you have to have money for us and for the remote sensing. So it's not a freebie.
So I have 2 questions. First, when I was trying to get my head around vegetation departure a long time ago, I just basically had to create an Excel workbook with all sorts of and just go through the calculations several times and watch how things played out. As you were working out the spatial ecological departure processes, did you leapfrog to that, or do you happen to have some game or toy I could play with to experiment in more abstract space to see how it works?
We actually had a meeting in Las Vegas, so because one of our staff is down there, and we had a 2-day brainstorming session on how to do this, because I was hell-bent, and we had a donor that gave us $10,000 or $6,000 of do whatever you want for science innovation money to do this, and we spent her money on that kind of stuff to actually develop this. So we actually did, there's an atomic science or atomic museum in Las Vegas, where we're like one door next at the DRI building, and we spent 2 days in a room figuring this out. And when the idea we had going in, Randy, how to do it was totally wrong, and we finally walked out of it with some gee whiz moments, and we figured out how to do it. And then we had follow-up workshop where it was brute force coding, with Sarah was doing the coding. We were saying, this is how it, so Kevin, Michael, and I, and she was literally coding as we went in R, how to do this with dummy examples and all that. And it was actually one of the most fun projects I've done, because this is pure R&D, let loose type of innovation. That's the stuff I like doing a lot. So
yeah, that
I
synergy
do wish that we had this workshop maybe 4 years ago. That would have been helpful for that situation. But I would like to do kind of an exploratory tool with the most recent results that we have, Randy. And if I can get that running and up on GitHub, I'll definitely let you know.
So the stuff I presented for the Tumbling JR, Sarah uploaded that several months ago to GitHub. It's already on GitHub, the code to do this. So, but she's constantly improving the code. So eventually it's going to be more Python and all that, but just realize, and this work may be published. So, we submitted a manuscript, and I'm still waiting on the decision from the editor. So this was the Tumbling JR work was submitted to the International Journal of LANDFIRE or something like that. Yes.
So
Randy, we only have 1 minute, but I really have to ask a question, Louis, which is, has anybody you've ever worked with just said, whoa, too much information?
Yes.
Yeah.
Oh, this is an important, thanks for asking that question.
Yeah.
So the Boulder Mountain, this is an important distinction, and you guys are gonna love this, the LANDFIRE folks. They just wanted one metric, ecological departure. So that's 670,000 acres, that huge landscape at high elevation. They said, and this was the Forest Service and the Utah Division of Wildlife Resources, and it was funded by the state of Utah with the Forest Service. Most of the money came from the state of Utah, and they had a declining population of mule deer there. And we said, well, we'll do a habitat suitability model for mule deer, in addition to, we always present ecological departure. And they said, no, we're tired of doing single species management. It's detrimental to the wildlife. And they said, and I'll quote, and everyone should listen to this, they said, all these species evolved under the reference condition. Therefore, we should aim as managers of wildlife for the reference condition, because these species, that's the system and the condition which they evolved. So the only metric they wanted, we offered them to do all this complicated climate change scenario. They said, no, we just want ecological departure, because we're finding that it is the best way to manage the land, even for single species wildlife management. And we said, correct. For once, I had a project where I could, when you have a landscape of that size, it is difficult enough to do. There's 3 of us working on this, and we're doing this part-time. We're doing 1 million acres with 3 people, and very much part-time, because we have other similar projects concurrent with this one. So the fact someone told us, take it easy and just give us something simple, that was wonderful. That was actually, finally. But that was the reason. They said ecological departure is the best metric we can find to manage wildlife. So.
All right. Well, thanks so much, Louis, for that. And we're kind of in discussion time. So if it's all right with everyone, I'm going to ask a question of Louis, Sarah, and Kevin that I think can cue up the rest of the discussion. So I'm going to kind of leverage our current conversation to launch into the discussion. So I am imagining Lisa Klusner out there. I think she's still here. Her wheels are turning. We work together a lot. And I know that both of us are always wanting to stretch and pull people along and get more value out of the science we can do. So with that, right now, we're at the space you saw earlier today, where we made this advance, mostly Lisa and team, of replacing one LANDFIRE input with something more relevant for their landscape. What would be the next thing we would add on? We cannot leapfrog to, spatial ecological departure. That's a huge leapfrog. But if we were going to take a step in your direction, and this applies to everyone here, what would be the next advance you would recommend to someone who's comfortable with ecological departure, they've got it down, but they want to do the next thing? What would be the next thing?
Well, what is the next thing you should do not you specifically, the LANDFIRE written large, the ARROS data center is go back to those biophysical settings and revise them. That's one thing I think should be high on the list, because basically everything we measure depends on how good those things are. And as you know, they're not always good. And so it depends on the modeling that was done years ago and all that. And use also go back to modeling, and you guys, so I'm telling you, LANDFIRE writ large, you're not for the individual users necessarily on this screen. Also, start using Sentinel 10-meter resolution. We have to start getting away from 30-meter resolution. Sentinel is free, and if you combine the two satellites, you can actually get great products. Google Earth platform, ARROS Data Center can do this stuff like in their sleep practically. So that's where I think the next big step is to improve the biophysical setting. Go to Google Earth Engine using Sentinel or whatever Sentinel data. And there's enough history of Sentinel now to actually do good things and remodel the biophysical setting. You already have data that allows you to correct your biophysics. If, like I said, if you have a black sagebrush system in current vegetation and it says that it should be Wyoming sagebrush, that is physically impossible. So if your current vegetation is the one that's ground truth, then you have to go fix with that data. There's already steps you guys could do to fixing things. But for people who are listening here, is that you should take advantage because this workshop was about ecological departure using tools you have, download LANDFIRE, but people should strive to take all that data in ecology and run their own simulations to do forest planning, for example, like we do with alternative A, alternative B, and C, and all that. And it's not a big reach to do it. You can do it non-spatially, but there is beauty to spatial simulation. And STSim is now built that if you actually can populate rasters and upload the rasters, even the LANDFIRE raster, doesn't matter. You have rasters for system and class and land ownership. It's not a big stretch to do the rest without getting too complicated. So it's you may need training or something like that if you're not familiar. And Apex does good training, and but I think people need to think more spatially about how to model stuff, not just non-spatially. So that's my advice. I don't know the other I know Kevin's on and Sarah's on, but it's and I don't know what Anna would say for Australia, but that's how I'm starting to think of. That would be a good step is to get into these aspects of,
Also, Tara, I see your hand up, so I wanted to acknowledge you and give you the floor.
Thanks. I think this is more of like a philosophical question or opportunity to just sort of think about time and time scales. Because the comment that was just made about how species evolved in pre-Europe in the time scale that matches pre-European colonization, that's not true. And I know that we have to, as managers, decide on points of reference, but I'm wondering about, instead of focusing on a snapshot in time, about a range of conditions that we know have occurred reasonably within the last 1,000 years, 5,000 years, 10,000 years, and is that even something practical to put into a management framework?
That's a great question. So the one thing I did not mention about these simulations is that the natural range of variability that we develop spatially for the spatially explicit stuff is actually with current climate. So it's the natural range of variability under current climate, and we've also done where we transform the historic, what I call the reference condition, but the historic range of variability with climate change scenario. So we actually apply to the simulations range shifts, where one ecological system dominated by like Wyoming sagebrush moves up the hill into Mount Sagebrush, it basically replaces Mount Sagebrush at the next higher elevation. So we actually transform the reference condition with current climate, but also with climate scenarios. Everyone tells us, well, the reference condition is going to change. We don't know how the species are going to sort out, but we know that some systems will have different species, but you'll probably recognize that the same systems. And some species just move up the hill, some go around the mountain, other things like that. We actually simulated that. So we're not obsessed in any of our projects with, you know, are we representing the reference condition 5,000 or one? We actually always define the reference condition in terms of the current climate. We just take the PRISM data from 1950 to 2022, for example, and we forecast it into the future. We do a stochastic weather generator. Kevin does that, stochastic weather generator, and we use the standard precipitation and evaporation index to influence this, but we're using future climate to define that. So we don't get hooked up about what it was and all that. And the managers are aiming for there's a goal, you know, there's a target far away over there, and they're shooting arrows towards that target, but they miss, but that's fine. As long as they're shooting more or less in that direction, that's what's important. No one wants necessarily, everyone knows you can't get back to that, quite that reference condition, except in a few cases. And that doesn't seem to bother the people we work with. So they're comfortable with that. And we tell them, this is the reference condition given your current climate. And people seem to be okay with that. So in our case, but that's I really like that question because we're rarely asked that question.
And there is a range of values, right? I mean, Louis, you've said you present averages of, you know, percent early or percent open, but because you do the Monte Carlo simulations 1,000 times, you have averages, you have variability.
Oh yeah.
Does that get it? Yeah.
Yes. And also we have actually Corey, in their publication on the non-spatial one, there's an error bar associated. So let's say it's early successional, 10%. Well, it's plus and minus. There's a mean standard error associated with that, or a variance or whatever. We have that. I just didn't show it. I just showed the variances in the spatial graph. But if you take that variance and you take those proportions, then you can do it. And not only that, well, we can associate a variance to the pixel. No, not to the landscape, to actually the pixel, and then we can do it, sum it across the landscape. So because variance is additive, and you can do that. And so there's a lot you can do with this, and we're just starting to scratch the surface, you know, on this.
All right, and then I wanted to Tara just tag on to I think what may have made you ask the question, and with your comment in the chat, I have also wondered about the statement you hear about species evolving. And I'm not an evolutionary biologist or a geneticist or anything like that, but I've sometimes wondered, like in our where I'm at, where highly glaciated landscape where the glaciers were treated 10,000 years ago. I'm like, 10,000 years? Meh. You know, is that really, did species really, quote, evolve in 10,000 years? I don't know how that lines up. So I just, at risk of triggering a big, you know, discussion about that, I wanted to just acknowledge your comment there, Tara, that I've had the same question. And I think that phrase can be thrown out a bit loosely. And I'm not sure myself as a biologist how I feel about that one. So I just wanted to tag that one a little bit. And there may be an evolutionary biologist here that's like, oh, 10,000 years is plenty of time for mammals to evolve to vegetation patterns, but I've wondered about that.
Yeah, I think it is a fun rabbit hole of a conversation to have for sure. And like I'm in the Puget Sound area of Washington, and we're in the same boat in terms of just glaciation history and those kinds of questions.
Right. Well, thanks for that, Tara. It is fun to step back into more of a biological framework, at least for a minute there.